we will focus on what Learnable obfuscation can offer and what Learnable obfuscation cannot offer, especially when it comes to security. And in the end, we will see two demos to show you how this technology was applied and especially how this technology failed in the past. So I don't think there is a special need for justifying the research on privacy-preserving machine learning. We have regulatory constraints like GDPR. We also have all kinds of setups in which there isn't a single party which holds all the data, but there are multiple parties, each holding a specific subset of the data. They need to proceed somehow to put this data together to train a machine learning model without compromising the confidentiality of the data. And I will give you an example, a practical example, where privacy and utility must function together. Imagine that imagine a scenario with 3 hospitals, for example, each holding data about a specific disease. And we need all the data from all 3 hospitals in order to train a machine learning model to help us detect that disease in the future. Obviously, a hospital cannot release this type of data because we are talking about patient data, we are talking about humans. A hospital is not legally, cannot legally release this type of data without affecting the individual. So we have to design methods to ensure that all 3 hospitals can put this data together somehow and train a machine learning model without compromising the confidentiality of the actual data. And when it comes to this method, we have two major classes. We have provable methods and non-provable methods. When we are talking about provable methods, we are talking about basically cryptography-based solution. Homomorphic encryption, in which the idea is that we encrypt the data, we put the data on the cloud, and the machine learning model learns directly over encrypted data and give an encrypted result back. We are talking about, in this category, about secure multi-party computation protocols, which are protocols that are designed specifically for the scenario in which we have multiple parties. Each party holds some data, and they all need to compute some function, in this case to train a machine learning model over the union of the data. We have differential privacy, which also guarantees us the security in a very formal way. Here the idea is that we add noise to the data, but we add a specific noise to the data. We add the noise to the data in such a way that in the end we are formally sure, we are 100% sure that the data cannot be denoised, just to give you an idea. And there are other methods, but the general idea is that in provable methods, we are talking about cryptography-based. We are talking about methods that have a formal mathematical proof that nobody in the world, whatever power it might have, cannot reverse the transformation to recover the original data. So you are mathematically 100% sure on the security of the data. The downside is that this type of methods does not really work in practice. So for homomorphic encryption, we have increased running times. For secure multi-party computation, we have a quite big communication overhead, and so on. On the other side, on non-provable methods, these are highly efficient methods, but in the current stage of research, most of these methods lack a formal security proof. And historically, it's been a game somehow. So somebody designed non-provable methods, then after a few weeks or months and so on, somebody else broke that method, and so on. So the current research landscape is actually a game. I design a method, you break it. I design another method, somebody else break it, and so on. But they are efficient. So in learnable obfuscation, we have three main techniques. We have what is called masking, mixing, and permutation. When we are talking about masking, for example, we are talking about taking the data and applying to each sample a consistent geometric transformation. So for example, in the case of images, imagine that you take each image and you add to each image a random image. When I take a picture of this class, for example, and I add a random noisy image, I get a random image, of course. So these are the masking techniques. Here the idea is that the transformation must be consistent. So if I want to train a machine learning model on multiple images, I have to add the same random image to all of those images. Then we have mixing, in which we simply create combinations. Now imagine that we have a data set with cats and dogs. By mixing, I mean we take an image of a cat, an image of a dog, we mix together and we give this mixed image to a machine learning model to learn it. Something like, if I have, like I said, images with cats and dogs, I create images in which I don't identify a cat or a dog. I identify something like 70% a dog and 30% a cat. That image doesn't make any sense. So in a way, it preserves the confidentiality. But when I give that image with 70% cat and 30% dog to a machine learning model, and I say to that model, look, here is an image, the label is not cat or dog, the label is 70% dog and 30% cat, the machine learning model will be eventually able to classify original images with cats and dogs, if it sees many such mixed images. And we have permutation like a side technique, which is usually applied with, in conjunction with one of the above methods. In permutation, the idea is quite straightforward. Imagine that you have an image, you take each row of pixel of that image, and you simply rotate each row of pixel 3 position to the right, something like this. So the general protocol workflow is as follows. I have some data, you have some data. We both agree on a particular transformation. Like I said, we both agree that we add to our images a random image. You know that image, I know that image, I add that image to all of my images, you add that image to all of your images, and we put this data together in a single server, so to say, in a single place. Then we came with the machine learning algorithm, and we put that algorithm to learn from the transform data set. And after the machine learning model learns from that transformed data set, we can both use the trained model on our data. Now here, I would like to emphasize a detail. We are not talking about, when it comes to learnable obfuscation, we are not talking about privacy-preserving inference. We are talking about privacy-preserving training. So the idea in a such protocol is to somehow perform a training over the union of the data, but when it comes to use that trained model, we are both going to use on our local data. So in my previous example, I put the transform images in the cloud, for example. You put your transform images in the cloud. We run the machine learning model. The machine learning model learns the transform data, how to classify transform data. And then we are both going to receive the trained model, and we are going to use locally. So we are not talking about performing inference in the cloud. We are going to talk about performing inference locally. So that's the general core flow of a such protocol. Now, the most important part in this story is, of course, security. And here I want to give you a brief intuition about how we see security in cryptography and how we see security in learnable obfuscation. So in cryptography, there is no middle way. So when it comes to encrypted data, an attacker cannot find any information about the plain text data. And a classic security game for this, for many encryption schemes, is the indistinguishability chosen plain text attack, in which we have, imagine that we have a server, we call that server an oracle, for example. That oracle produces encryption of the data. So it's like we have, in the cloud, we have something that encrypts data for us. We don't know the encryption key. Maybe we know the method. We don't know the method. We usually know the encryption algorithms. But just to keep things concrete, imagine that we have some server that returns AES encryptions with a particular key that we don't know. What do you mean when we say that that encryption scheme is secure? If I query that server multiple times and I receive encryption all the times, and in the end I am not capable of distinguishing between encryptions, it means that that ciphertext is secure. So I can say something like encrypt, this is an apple. Encrypt, this is a car. I get two ciphertext back. Then in a query phase, I have to choose, I receive from the server a ciphertext. That ciphertext encrypts either this is an apple or this is a car. And if I'm not able to say what plain text does that ciphertext encrypts, even if I previously query the server for many encryptions, even on those sentences, means that the encryption scheme is secure. This is a very strong security definition. In learnable obfuscation, the things are not that strong because, like I said in the previous example, from a cryptographic perspective, an attacker is not able to distinguish between two encryptions. Now, in learnable obfuscation, think about these scenarios. I train using a learnable obfuscation method, either MNIST dataset or CIFAR-10 dataset. MNIST dataset is a very simple dataset. It's a dataset with handwritten digits. The images are grayscale, and usually with very simple learning algorithms, we get accuracy like 99% and so on. CIFAR-10 is a slightly more complicated dataset. We have color images. We have images of 10 classes, multiple objects, and so on. Usually when we learn over CIFAR-10 dataset, we get with reasonable algorithms an accuracy of 17, 80%, and so on. This means that an attacker can use this difference in order to distinguish which dataset it's now learned from. So to continue my previous example, I put some transformed data, for example, MNIST, on a server. The attacker observed the learning process, and it observed that the accuracy in the end is 99%. The attacker can use that information without knowing the underlying data to determine that the transformed data are actually very simple to learn data, like MNIST. So from this perspective, a learnable obfuscation method cannot ever be as secure as a cryptographic-based method. But things are not that terrible. We cannot achieve that strong security definition, but maybe you can achieve some other goals. The idea and the main drawback of learnable obfuscation right now is to be able to formally define what are the goals of the attacker. So, all right, we cannot achieve 100% security as in cryptography, but maybe we can define some other goals. The idea is to be able to define those goals and to be able to prove that the obfuscation method achieves those goals. And several such goals are, for example, data reconstruction. We don't care about indistinguishability and so on. We care only about that the attacker should not be able to determine the original data. So if I put some transformed data on a server, I don't care if the attacker deduces that those data are simple to learn or more complicated to learn, if they are grayscale images or color images. I don't care about this stuff. All I care is that the attacker should not be able to reconstruct the images, the exact images. Another type of goal is membership inference. This is particularly suitable for healthcare scenarios, for example. In this type of goal, I don't want the attacker to be able to determine if a particular sample is part of the data set. So if we have multiple patients that takes an X-ray scan, for example, and we transform the data and we put that data on the cloud for an algorithm to learn, I don't want an attacker to be able to say that the X-ray of a particular patient is in that data set. And of course, we have reverse engineering here. I don't want the attacker to be able to design a method to reverse my transformation. So, like I said, right now we don't have formal security definitions for learnable obfuscation method, but we have some sort of definition, and those definitions are usually based on informatic theoretic measures, or are based on, let's say, some methods that guarantees partial goals. So, for example, there are learnable obfuscation methods that guarantees that an attacker cannot reconstruct the original data, but they don't guarantee that an attacker cannot perform a membership inference attacks. So we have some privacy, we have some formal privacy guarantees, but they are not in full. Right now, there isn't a learnable obfuscation method with that formal privacy guarantees to guarantee all three goals from the previous slide. So, like I said, this battle is not entirely lost, because we have a recent paper, it's a paper from last year, that tries to formalize as much as it can this learnable obfuscation method. And in a nutshell, basically, how they model security they model security in the following way. So, like I said, a general learnable obfuscation method is composed from 3 building blocks. We have masking, adding that random images. We have mixing multiple samples, images together, and we have permutation. What this paper is about, they design a general learnable obfuscation method by combining all 3 building blocks. And they were able to formally prove that an attacker cannot reconstruct the data, so it's only about the reconstruction of the data. An attacker cannot reconstruct the data if the attacker does not have enough examples of plain text and obfuscated data. So it's like something, I apply this obfuscation method to my images, and I can be 100% sure that if an attacker does not get more than a particular threshold of example, I am secure. An attacker cannot be able, no matter how powerful that attacker is, cannot be able to reconstruct the original data. So now let's see 2 case studies. We are going to talk about NeuralCrypt and InstaHide. So NeuralCrypt, it's a masking technique that simply said that, all right, you have some data, I have some data. We generate a random neural network. We initialize that random neural network with random weights, but we are both going to use the same neural network, and we process our images through that neural network. Then we put the transform images on the cloud, and we are going to learn over transform images. So the main idea of this method is to use a random neural network. But here I want to highlight that and this is very important, especially for the attack, the same neural network must be used to all images. So I'm not going to use a neural network on this image and another neural network on this image. I'm not going to use a neural network and you are going to use another neural network. We both agree on the same neural network and apply that random neural network to all of our images. And actually in the paper, and this is funny, the authors formally proved that their method is equivalent with one-time pad. So it's information theoretic secure. And it's a valid proof. It's a mathematical proof that no matter how powerful the attacker is, using a random neural network, the attacker will never be able to reconstruct the original data. And it's funny because the theorem is correct, the proof works, but in reality, this system is not secure. Because when they formalized the security and they proved the security, they didn't take into account that an attacker might obtain a very small subset of transformed data. So they modeled the security in a scenario in which the attacker does not know any original data or any transformed data. And this is not applicable in real world. The reason is simple. Imagine that you have some private images. You want to train a machine learning model for object classification, for example. And you have your private images. Let's say you have 1,000 images. Usually when you train this system, you are trained to perform a task. You are going to train the system to solve a real problem. And to do that, you have to get a good classification accuracy. And to get a good classification accuracy, usually over your 1,000 private images, you are going to put in the training process some public images, because we have very large public data set of images, like ImageNet, GFART, and we're talking about 10,000 of images, and you are asking, all right, it doesn't hurt. I have my private images, 1,000 images, but I put in the training another 10,000 public images just to get the algorithm to perform better on the task. So an attacker can exploit this and can get since you are using public data, an attacker, it's reasonable to assume that an attacker might get a sample of your data. The second system is InstaHide. The InstaHide is based on mixing. So we take, let's say that we have a data set of images. We are going to form groups of that images, and we are going to perform mixing on each group. Like I said in the introduction example, if I have a data set with cats and dogs, I'm going to artificially create images with 50% dog, 50% cat. And what InstaHide add to this step is a random sign flip. So I take an image of a cat, I take an image of a dog, I create an image which is 50% dog, 50% cat, and then I randomly flip the sign. And the assumption of InstaHide is that randomly sign flipping is going to protect the entire mechanism against attacker, but this is not so. In InstaHide, we also have, and it's again funny, we have a theorem which proves that InstaHide is secure. And just to give you an idea how that mixing works, when we are talking about mixing, we are talking about performing weighted sums. So I take an image of a dog, I take an image of a cat, I generate some random weights, 50-50, let's say, and I'm going to determine a mixed image by computing the first weight times the first image plus the second weights times the second image. So mixing it's about performing, that is confusing. Mixing it's about performing weighted sums. And in cryptography, we have a hard problem. We have a problem for which researchers were not be able to find the polynomial time algorithm, and that problem is called the subset sum problem. And in the InstaHide paper, the authors proved that if somebody would break InstaHide, then that somebody, that attacker, would be able to solve the subset sum problem, which is hard. And that was their security proof. So if you break InstaHide, it means that you are able to solve the subset sum problem. And since that subset sum problem is hard, so no one can solve it, it means that InstaHide is secure. That's the proof. But again, InstaHide was break. For the same reason, neural crypt was break. Because in both system, neural crypt and InstaHide, when authors modeled the security, they started from the assumption that no one can ever gather a small subset of transformed data. So they start from the hypothesis that an attacker will not have any single pairs of plain text image and transform image. And this is very unrealistic. So I'm going to move to the demo. So the demo is performed on MNIST dataset. Like I said, it's a dataset with handwritten digits. I previously ran the cells. So here is, like I said, the idea behind neural crypt is to apply a random neural network to every image in the dataset. And here I instantiated some random neural network. It's actually a linear one, so it's a very simple neural network. And this is the result. So I have the original image of an 8. I apply that random neural network, and I get the transform image. As you observe, the transform images apparently do not leak any information about the original image. So they are just noisy image. And this is intuitive because we use a random neural network. So we basically took each original image and we multiply it with something random. And of course we get noise. But again, I want to emphasize that we apply the same neural network to all images. I emphasize this all the time because for both cases, NeuroCrypt and InstaHide, this is what get the system to fail. Now, here in this cell, I train a neural network. So we are talking about this neural network. It's a simple classifier over the transformed data. So it's a classic neural network with several layers. I train it on transformed data, and I get an accuracy of 96%. And it's expected for this type of neural network and this type of data. Now, when we test the trained neural network, previously I trained the neural network, now I want to test it. I want to classify this image of 3. we said in the general protocol workflow that we first transform the data, then we put all the data together, we make the algorithm learn on the transformed data, and then we use the model locally. The catchy part is that we use the model locally on the transformed data. So in order to be able to use the previous neural network that I trained in the above cell, here, this neural network with 96% accuracy, in order to actually use the neural network, I have to use it on transformed data. So if I plug the original image, that free, in the neural network trained over transformed images, I'll get a label 6. And this is, of course, incorrect. But if I first transform the image and then I use the neural network trained over transformed images, I get the correct label free. And now the attack. NeuroCrypt indeed has a very nice theorem with a very nice proof. The theorem and the proof are both mathematically sound and correct, but they assume the attacker does not have access to any example of original and transformed data. And like I said, this is unrealistic in real life. And in this cell, I suppose that the attacker has access to only 50 pairs of original and transformed data. So just to give you an idea, the training size data set, the MNIST training size is about 60,000 images. And here I assume that the attacker only gets 50 examples. And what the attacker will do, will basically train a neural network on that small subset of examples. So the attacker gets some example of original and transformed images. He trains a neural network on that small subset of pairs, original and transformed images, and the attacker would be able to use that neural network to recover the entire transformed data set. And just to give you an idea how this looks, so initially we transform a data set of 60,000 images. And then I assume that the attacker gets access to only 50 pairs of original transformed images and train a neural network on only that very small subset of 50 pairs. And here I test the neural network trained by the attacker on test data, so data that the network didn't. So in the training stage, and like you see, I get a quite good reconstruction with just 50 images. So all right, it's not the best quality, but I can distinguish most of the features of the images. And this happens only with 50 pairs of original and transformed data. And now to jump to the demo on Mixup. Like I said, the idea behind Mixup is to perform weighted sums. So I combine images. Here I don't use MNIST, I use GFAR10 dataset. And this is how mixing looks like. With I restricted the dataset to only 3 types of images, just to run faster for this demo. So here, as you can see, I take an image of a car and then an image of a bird. I associate it with the car a weight of 34%, and with the bird I associate a weight of 66. And then I computed this image, and in InstaHide, don't forget that once we compute this sum, we also randomly change the sign of each pixel. I get a noisy image. So this is what InstaHide is about. So we simply perform weighted sum. Then I train a classifier, a simple convolutional neural network over the transformed data set. And I get an accuracy of here 80%. And yes, 80%. This is a quite good accuracy for this type of data set. And here, what I also wanted to emphasize about InstaHide is that I said that InstaHide is also a very nice formal guarantee. So in the paper, we see a theorem which states that if you can break InstaHide, then you can solve a hard problem that nobody solves. So it's absurd to assume that you can break InstaHide, so InstaHide is secure. That's the proof it's about. But they assume that the weights are secret. And in reality, when you implement InstaHide, the weights are not secret, because in order for the algorithm to learn on the transformed data set, I must say to the algorithm that here is a mix-up image, but I have to specify to the algorithm that that image is 58% bird and 42% airplane. No, sorry, 58% airplane and 42% bird. So I have to give that information to the algorithm in order to be able to learn. So the weights are public, and the attacker can exploit the weights by simply solving a linear system of equation. So it's actually high school math. InstaHide, like I said, it computes sums. It's like having each image, it's an unknown. And the goal of the attacker is simply to solve a linear system of equations. So once the attacker has access to the weights, and has access to the weights because the weights are leaked by the labels, the attacker will be able to simply solve. So in this scenario, unlike the neural crypt, the attacker doesn't train a complicated neural network. The attacker simply solves a linear system of equation. And the result is quite good. And here is an example. So the part with the randomly signed flips, it's dealt by the attacker simply considering the absolute value of each pixel. And in the end, the attacker will be able to recover the original image up to the sign. So in this recovery image, as you can see, it's a good image. We distinguish many features. For example, here I know that it's a car, but the sign of each pixel in this image, it's somehow perturbed. So I'm not sure about the sign, but there are other methods that can improve this part of coloring. So to summarize, learnable obfuscation is indeed very efficient. You saw that it's about computing sums or applying random neural networks. So we're not talk about complicated encryption schemes and so on. So it's efficient, it works, the algorithms can learn on the transformed data, but we are not 100% sure on their security. And you saw this in NeuralCrypt and InstaHide. The irony is that both papers, NeuralCrypt and InstaHide, has theorems that actually prove that their system is secure. But if those theorems are not founded on the right assumptions, on realistic assumptions, they, of course, will fail. And they fail like we saw in the demo. But this doesn't mean that we have to remove this type of methods from our memories, because, like I said, last year it was released a paper that actually gets some hope in the entire field. But the idea is that after all, to be cautious with what we use. So we can design learnable obfuscation method, but we have to be very cautious with them. We have to look closely at what assumption they made when they are designed, what assumption they made when their security is proof, and so on. So the idea is that it works. We are not 100% sure on their security, and we have to be cautious with this type of methods. So that's all. Thank you.
Are there any questions?
Hello. From my experience, the main issue with privacy-preserving AI is to convince data owners or whoever has the data to actually use your algorithm. Based on what I've seen, in which situations could you convince a user to actually use something like this, now that you just showed how easy it is to attack it? Thank you.
Thank you for the question. So right now, I won't be able to convince anyone to use this type of methods. So if you need privacy-preserving methods, I will highly recommend secure multi-party computation. It has a large communication overhead, but it's not that bad on running time. So for a small data set, it can be used. But for learnable obfuscation, it's very promising. The paper from last year has very good results in theory. It shows that in the future we will be able to formally guarantee some security properties of learnable obfuscation, but for the moment it cannot be used in practice.
Hello. In the NeuroCrypt demo example, if you increase the number of samples for the attacker to more than 50, does that improve the quality of the recovered images?
Yes, and I think it's quite fast to show that. So here, if I can get 100, yeah, so it's better, maybe 500. We also have to increase the training gap, but as you can see, the images get better. So from 50 samples, which were noisy, here the quality is better. So yes.
So hello, you tested this for image classification like on MIST database, but what happens if you want to obfuscate images from, I don't know, with pattern recognition to identify like tumors in image MRI images? This will work, or your obfuscation will damage the learning? Because, you know, in a X-ray maybe it's more difficult to identify patterns than say this is a cat, this is a dog. It works, this method, or not?
It will not hurt the accuracy. So historically, all these type of papers on learnable obfuscation performs experiments on data sets starting from MNIST to ImageNet, just to prove that increasing the complexity does not hurt the learning process. So learnable obfuscation does not really hurt the learning process. We get good accuracy. Of course, that we have to compensate somehow. So in the case of instant hide, if we train for GFAR 10, for example, if over plain-text data, I have to train that a neural network for, let's say, 100 epochs. Using InstaHide, I have to train larger neural networks on 200 epochs. So we have to compensate to the model, but eventually we'll learn because the features are not there. The main idea of learnable obfuscation is to prevent the attacker to recover the data or to perform membership inference attack or to achieve some security goal. But let's say, utility idea of learnable obfuscation is to preserve the learning features. So in InstaHigh, for example, if we take weighted sum of the images, the features are there. In NeuroCrypt, for example, when we apply the same neural network to images, the features are there, but they are transformed. And when we transform the samples at inference time, it will work. The question is about security.